Welcome everyone to this video. Today we are going to start with a new topic, that is waves. As we have already finished with the chapter of kinetic theory of gases, we want to move forward uh, with new things. So our approach in this lecture is going to be question first. That is, we want to learn whatever concepts which we have, and whatever formula which we have through questions only. So let's begin. So first of all, when we talk about waves, what is the first thing which comes to our mind? So waves, something somewhere reminds us of a beach, or it can remind you of a wave in the crowd, in a cricket stadium, how they raise their hands up and they form a wave of those raised hands as the wave comes to them, and basically it shows that human collaboration and ingenuity power. So basically, wave is a transmission of information. In that example, that you have to raise your hand, that information is passed through some sensory input to the human sitting right beside you. In physical world, waves is transfer of energy or momentum. This transfer of energy and momentum can take place through two ways, either through a medium or without a medium. When the wave travels from one point to another and it requires that medium, then it is called a mechanical wave. Um, and otherwise, when there is no medium requirement, then it's called a non-mechanical wave. So the phones uh, receive that signal through mobile tower. That is a non-mechanical wave. Um, we are seeing each other through light. You will read it later. Light is also a electromagnetic wave which does not require medium. How do you know that it does not require a medium? Because light travels on Earth as well. Light travels in our surrounding, which is basically filled with air. Light travels through glass. Glass is also a material medium. So how do we know that it is not a mechanical wave? We can infer by taking the example of space. In space, there is no medium. The light can travel through that. So we can infer that no medium is required for light. So through our common sense only, we can arrive at these judgments. In this chapter, we want to achieve uh, the knowledge of how to study the effects of a wave on the particles when it travels through a point. So first question which we have is y is equal to a naught cos squared 2 pi f naught b minus 2 pi x by lambda. So this is a wave equation. In this wave equation, this term y uh, represents particle displacement. This is written particle displacement. What does particle displacement mean? Particle displacement implies how much the particle has moved from some certain fixed position uh, when t time has passed and at a distance x from where we have started measuring the position. So this y shows that the particle would be getting displaced in some direction. How much that displacement is going to be given by the left hand side of this equation. In this equation, there are lots of terms. There is a naught term, there is 2 pi, f naught, t, and so on. So at first, it can be little, it could uh, looking of no sense. Would be making no sense at all to you. You would be showing that you would be even thinking, why have I written it? Just to confuse you or what? But the point is not that. Point is that we want to learn what are different terms. So this A naught is called the amplitude of the wave. Amplitude means that when you, let's say, shout at someone, so we say that amplitude of voice is high. And when we talk with our loved ones, we are talking usually in a low amplitude. When your mom speaks to you, it could be a high frequency voice, and when your father speaks to you, it could be a low frequency voice. All that is encoded in this wave. Obviously, they do not speak monotonically all the time, but if they were to speak at some certain instant, at a single instant, they will be having some certain frequency of speaking. You would be also having that frequency of speaking. By modulating our frequency, we communicate how we are feeling. We communicate what we want to do. We communicate how we are able to uh, absorb the information provided to us or what is happening in front of us. This T stands for time, which is one of the most important part of a wave. How much time has a wave taken to arrive at some certain point, or after the wave has started, how much time has passed. You can say time elapsed, something like that. X is called the position. Okay, so all these are the things which are part of a wave. Here the question is, what is the amplitude of the wave? What is the uh, frequency of the wave? And what is the wavelength of the wave? So if this wave had been a wave in which cos 2 pi f naught t and this whole term should have been there, then our answer would have been uh, straightforward. That is, frequency would have been f naught and uh, the wavelength would have been lambda naught. So that would have been our answer to the question itself, that what is amplitude, what is frequency, and what is the wavelength. Frequency and wavelength are also important in the sense that when you're talking about mobile signals, so you would have seen that government is auctioning this much government band of frequencies, like 900 megahertz to 600 megahertz. This band of frequencies have been auctioned. So that is directly related to this particular uh, physical quantity. So that is what frequency is. So it's pretty important thing. Wavelength means that what is the distance between two crests of a wave. So if a wave, so if we have a wave like this wave is traveling through a point, which is like a difficult thing to understand. How does wave travel through a point? Like if we are looking at a wave, it almost seems like that कि, only some mass is traveling, right? Like those crests are मतलब, going forward. So it feels like that कि the wave is traveling in forward direction, which is correct. But is mass traveling as well? So, so the point is that कि, the up and down movement of particles is what is happening. When the particles are moving up, they are gaining some kind of energy. How they are gaining that energy is from some other kind of energy. Okay, so that means that there is a transfer of energy from one form to another. Definitely, when the wave has started, we would have supplied some energy to make the wave happen. But right, then we say that at a single point, the wave is getting its energy from the particles behind it, and that energy which it is getting, it is divided into two forms. It is divided into how fast the particle is moving, and it is divided into how far the particle is from some mean position. How far the particle is from mean position shows the potential energy of the particle. How fast the particle is moving shows the kinetic energy of the particle. So, what you want to say is that these energies are what we are seeing as the particle is going. Right. So, which means that the mass has not to go and do the job of providing that energy to that particle in front of it. The mass itself has not to move in direction of wave. It creates that condition. It creates that force which transfers that energy to the particle in its neighborhood. And the same particle does the same thing. Um, so, a good example or good analogy would be, let's say you are in a line. Okay. Nowadays, people don't stand in the bank queue. But if you go to uh, some bank, it is possible that you might find a queue. Or let's say you are going to attend a concert of, let's say, uh, Coldplay, and there is a line. Now you are at the back of the line, and your friend is annoying you that let's get in the seats first, and so on like that. So you push the person in front of you. Now you have not moved, but the push you have created has uh, displaced the person in front of you. That is what happens. You're not going forward. Only the push you are providing that goes forward. Coming back to our question, minus 2 pi by lambda into x. So to convert such a equation where we have cos square instead of a simple cos or sine function, we can use a half angle formula. So after using the formula, which is cos square theta. So cos square theta we can convert by using 1 plus cos 2 theta upon 2. So what happens is that this angle it gets doubled. So square, this will become 4 pi f naught t. This 2 it comes within. So this is our final result. Notice that there is a plus 1 here. So in this plus 1 sign, this is a fixed quantity, right? Um, so what should we do about it? We learned that the thing which is beside cos is the amplitude. So we should stick to it. Okay. We'll say that this is some constant quantity. So it is not showing any variation with position and time. It just shows that when the particle will have this whole thing to be, let's say, uh, pi by 2. Let's say this whole value comes out to be pi by 2 because I said that. So this will become cos pi by 2. Cos pi by 2 is 0. So this will become a by 2. So this means that whenever this whole quantity becomes pi by 2 or 3 pi by 2 or integral odd multiples of pi by 2, then this will term will keep on going to 0 again and again. So this quantity is like a constant over which this whole term is varying, right? You can imagine like that in a SHM what happens? A particle is getting displaced from the mean position. So there is a term which is varying and there is a term which is constant. Same thing is there. Here this term is a constant and this whole thing is varying. So we'll stick to the idea that this half it can go inside. So as this half goes inside, this is become a naught by 2. So this is my amplitude a naught upon 2. Then we have frequency. What would be the frequency? Frequency is represented by the coefficient of uh, t term. So this whole term we can compare with 2 pi f. This 2 pi comes from the idea uh, that we have the complete wave. When we go through complete wave, the phase change is 2 pi. So this 2 pi is here. Okay. 2 pi f is equal to 4 pi f now. If I take what the frequency is f, that would be some 2f. Next we have wavelength. In the same way, I can compare this 4 pi by lambda with 2 pi by lambda naught. So this lambda naught is simply lambda upon 2. Is it lambda naught? Yes, this is lambda naught. So we are trying to find lambda. So lambda is equal to lambda naught upon 2. So I think for this video only this much is enough. Next time we'll continue with a new idea. Thank you.